Aloha, my name is Marley Chertok, and I'm a PhD student at the University of Hawaii at Manoa. I'm honored to have been selected as the 2022 recipient of the Toby Lee ARCS Award in Earth Sciences. My work revolves around uncovering the characteristics of ancient lava flows on the moon. To do this, I look at blocks on the lunar surface like the one shown here with an Apollo 17 astronaut for scale. Blocks like this are ejected by high-speed meteorites that strike the lunar surface and break up these cooled volcanic deposits. Unlike Earth, the moon lacks an atmosphere, so solar system processes are excellently recorded and preserved here without wind and water acting to degrade them. The moon serves as a natural laboratory that stores a wealth of information about the solar system. The story of volcanism on the moon begins with enormous impact craters that were formed about 4.1 to 3.8 billion years ago, when large meteorites were more plentiful in our solar system. Between 3.8 and 1 billion years ago, lava infilled these low elevation impact craters through multiple volcanic episodes. These lavas cooled and hardened, forming dark basaltic rock, which is also extensive here in Hawaii. Throughout the process of cooling, meteorites of all sizes are continuously striking the surface, forming craters and grinding up our cooled lavas into a powder and mixing it. This process of grinding and mixing over billions of years buries the original lava flows beneath a thick layer of fine, unconsolidated lunar soil. This is the moon that we know today, separated by dark regions called the mare and bright regions called the highlands. The lava flows we're interested in are buried deep beneath the surface of the moon, making them hard to study. But because we have impacts on the moon, they probe deep enough to expose lava flows. In this figure, the impactor on the left has ejected blocks of the original lava flow. I study these ejected blocks to better understand volcanism on the moon. I've collected approximately 15,000 craters on the moon in different volcanic regions. Then I used remote sensing data set that measures the heat stored by rocks during the lunar night. This data set is known as rock moments, and it is collected by an instrument called Diviner on board the Lunar Reconnaissance Orbiter. Next, I extract this measurement from the ejected blankets of my craters. This figure shows an anomalously rocky crater, and as we zoom in, we see rocks in and around the crater consistent with the bright red colored pixels. There are different lava flows on the moon. Some produce rocks, like the sample on the left, that are stronger and more resistant to impacts. And some produce rocks, like the sample on the right, which are weaker and are more likely to crumble upon impact. Regions on the moon with fewer rocks ejected from impacts are more likely to have weaker lava flows deposited, because the rocks break apart when they're impacted. My study had found that the lava flows beneath the craters are actually varied. The ancient lunar lava flows are showing response to meteorites. This work will identify regions of unique mare volcanism that may be interesting landing sites to explore. This work will also further our scientific understanding of the history of lunar eruptions and the physical properties of lavas on the moon. Thanks for watching.